Hi everybody, it's Mr. Eisner and I'm going to be doing the videos for the rest of the year. So we're going to start with trig equations and hopefully you've been keeping up and staying healthy and doing all of the right things. So here we go. This is part one. There's going to be a second half to this week. So here we go. Let me move ahead. All right. So what we're looking at here are trig equations, and this is a trig equation. It's just good old trig solve for x. Now, it does say no restrictions, and we'll talk about that in a second. In order to solve sine x is equal to 1/2, we're basically going to do what you did with inverse functions, and that is look for the angles that make the sine equal to 1/2. And we could rewrite this in an inverse kind of way by saying x is inverse sine of 1/2, and that's okay, but we really don't need to do that. Just think backwards. So for what angle does the sine equal 1/2? Think chart, and the answer is pi over 6. So it seems like we would be done that x is equal to pi over 6, but this is a no restrictions problem, and you won't see many of these, but you might, which means we have to do a number of things. First, we have to consider all the quadrants, not just quadrant 1. And if you think about sine, when is the sine positive? It's positive in quadrants 1 and 2. So we already have our quadrant 1 answer. That's pi over 6. We need our quadrant 2 answer. So I made a little sketch. Here's pi over 6 as a reference angle in quadrant 2. The angle to get us there, standard position, is 5 pi over 6. That gets us two answers, pi over 6 and 5 pi over 6. But we're still not done, because no restrictions means not only one circle, but all the circles. So we have to consider all the unit circles. The easiest way to do that is just recognize that if you have any answer at all, if you add 2 pi to it, you get the same trig values. If you subtract 2 pi from it, same trig values. So if we simply take an answer we have, like pi over 6, and do a plus 2k pi, where k represents an integer, then this gets us all circles going forward, backward, left, right, all of them. And 5 pi over 6 plus 2k pi, there's all infinite answers. So what happens if we move it a little bit, let's move me over here, and say, all right, let's do the same problem with one little difference. Now x has to stay between 0 and 2 pi. Could equal 0, doesn't equal 2 pi, right? Doesn't equal 2 pi. So difference, we've already solved the problem. Same problem, we got our pi over 6 and our 5 pi over 6, and we're done. Because there are no more unit circles to consider. The next type of problem I call less basic. It's similar with one twist, and it's a complicating twist, and it's that there'll be a coefficient in front of the x. So for example, cosine 3x is equal to -1. Now you might recall way back when we did transformations that one of the transformations we did was, if you had y equals f of x, what happens if you have y equals f of bx? So you might recall when you have a b coefficient on the inside, it was a horizontal compression or stretch. If b was greater than 1, we had a compression. And that's what we have here. This isn't cosine x, it's cosine 3x. So it's a compression by the factor of 3. And visually, we'll look at the problem on the next page, but visually, here's cosine, max, 0, min, 0, max, and we go all the way through. So here's our cosine graph. I have a value set here, at the wrong value, set that equal to 1/2, should be -1, that's okay. But we're just looking at the graph itself. And the graph compresses. So what was one period taking out to 2 pi, now that very same period is compressed by a factor of 3. In fact, we get 1, 2, and a third period, 3 full periods out to 2 pi. What does it mean? It means any solution that we would have had here now shows up 3 times between 0 and 2 pi down here. So we're going to be getting 3 times as many solutions. Let's see how that plays out. So Here's the process. We're trying to solve the less basic cosine 3x is equal to -1. What we'll do instead is solve the problem with a theta instead of an nx. So replace 3x with theta. Cosine theta is -1. There's only one theta that works for us, and that's pi, because cosine pi is -1. So we've solved the less basic problem, or the more basic problem. Now we're going to bring it back, and theta, well, that was nx. So instead of theta equaling pi, now we're going to set the original 3x equal to pi. Here it is. Divide by 3, and x is pi over 3. So pi over 3 is actually one of our solutions. But remember, what was one solution in the original becomes now 3 solutions because it's 3x in the more complicated problem. So what do? We need to get the new period. And we've talked about this before. The new period of a trig graph is the old period divided by that coefficient, which we're calling b. 2 pi divided by b. And that's 2 pi divided by 3. That's the new period. In other words, in the graph that's compressed, instead of the period being 2 pi, the period is now 2 pi over 3. So we're going to have to take any solution we had here, and if we add the period to it, it gets us the very next solution. And we can keep doing that and getting additional solutions. So here we are. So we're going to start with our pi over 3. Here it is in red. And we're going to add 2 pi over 3 to it. So that gets us 3 pi over 3 and then 5 pi over 3. And I could go to 7, but that's bigger than 2 pi. 6 would have been 2 pi. So we stop. 3 solutions, and we have our answers. We're done. Let's try another one from scratch. Okay, this one's a little different because it's 2/5, but the process holds. First thing we do is we replace 2/5 with theta. Solving cosine theta is 1/2. Now the original, most basic solution is theta is pi over 3. That's reverse the chart. But we know that cosine is positive in quadrant 1 and quadrant 4. So I need to look at pi over 3, the reference solution, in quadrant 4. That's coming off of the 6 pi over 3. So that gets us solution number 2, 5 pi over 3. But remember, it wasn't theta, it was 2/5 x. So take 2/5 x, set it equal to pi over 3. In this case, we'll multiply by 5/2, both sides, to solve that. And x is 5 pi over 6. For 2/5 equals 5 pi over 3, same process, gets us 25 pi over 6, which, by the way, is way bigger than 2 pi. That's too big. So we really only have one solution. Remember, when the coefficient here is less than 1, that means that it's a stretch. The reverse happens. Instead of one solution, this graph stretches out to a point where we may actually lose original solutions because they stretch outside of the original 0 to 2 pi. In this case, that's what happened. 5 pi over 6, that's it. Sine 4x is negative root 2 over 2. Solving sine theta equals negative root 2 over 2. When is the sign negative? Quadrants 3 and 4. Keep that in mind. Our reference angle solution, ignoring the negative, is pi over 4. We need to then take pi over 4 as the reference, put it in quadrant 3. That gets us 5 pi over 4. We go halfway plus the extra. Putting the very same reference into quadrant 4, here it is, leads us to 7 pi over 4. Because remember, we've got this 8 pi over 4. That's our 2 pi sitting off here. So we're going to subtract that away. There's my 7. So that gets me my 2 preliminary solutions. Then again, we're going to take our original 4x, set it equal to the 2 solutions, dividing by 4 gets us now 2 real solutions, 5 and 7 pi over 16. Finally, and this is just a mechanical process, we're going to take the new period. Well, the coefficient was a 4, so the new period is old 2 pi divided by 4. to get a common denominator so that I'm able to more easily add to my starting points, I'm going to multiply by the 4s and get 8 pi over 16. So we're going to start with our 5 pi over 16. Here it is, our first solution. Start adding in our new periods. Get 13, 21, and 29, stopping because the next would be too big. Then I go back and pick up 7 pi over 16, do the same thing, adding in my 8 pi over 16 periods. Total of 8 solutions, which if we think about it, we had 2 back here, times the 4 because of the compression, 8 solutions. Next up, I think this is our last example for part 1. Tangent to 5x is equal to 0. So part 1, we replace 5x with theta. The only solution for tan theta equals 0 is theta equals 0. Which is nice because when 5x equals 0, x equals 0, and that's my 1 starting off solution. And we divide by the 5, we still get 0. The new period, well, a little different. Tangent's period is only pi. So we start with pi divided by the coefficient 5. The new period of this tangent graph would be pi over 5. So we take our initial starting point of 0. Here it is. And we just start adding pi over 5s until we reach 2 pi. That's when we stop. So we start adding pi over 5s and we get pi over 5. And then 2, 3, 4, 5. Yeah, that's just pi. Leave it alone. 6, 7, 8, 9. If I went another, I'd be at 10 pi over 5, which is 2 pi. But remember, not equal to that side. There it is, 10 solutions, which is what we would expect. Here's a little graph of tangent, and we know what that tangent looks like. We get 2 solutions initially here. This is not, well, it actually would be a solution because we're okay there. That's just pi. But it takes 2 periods to get that, and then we multiply by our 5, just to see what's happening. That's it. That's part 1. There's a few more types of problems to take a look at. I'll do them in a different video. So I'll see you on the other side.